Okay, we are going to take a look at section 11.2, which is limits and continuity. Whoa, hold on. In 3D. So a lot of the things that you've seen in 2D will apply in 3D, but kind of sometimes in a weird way. Okay, so a lot of your theorems about limits and continuity will look similar. We're going to talk about the squeeze theorem in 3D. But then, just like any of our other 3D stuff, there's always going to be those weird little things that make it maybe a little bit more difficult. Okay. First thing, you will have three notations for limits that you might see. We have the limit as xy goes to ab of a function. Okay, equals L. You might see it written as the limit as x goes to a and y goes to b, like that. I think that's the way I learned it. Okay, and you might see something a little less likely. Fxy goes to L as, I'm just running out of room here, so I'm going to go to another line, but it would be right next to it. Xy goes to AB. Okay, they basically all mean the same thing. All right. We also have your whole idea of limits existing. So if f of xy goes to L1 as xy goes to AB along a path C1, and f of xy goes to L2 as xy goes to AB along a different path, C2, where L1 does not equal L2, then your limit as xy goes to AB of f of xy does not exist. Okay, it's kind of like in 2D, when if your left-hand limit and your right-hand limit didn't match, then your limit didn't exist. Okay, now we're coming at it from any direction. So if your limit coming from one direction doesn't match your limit coming from another direction, then that limit doesn't exist. So it's much easier in 3D to prove that a limit doesn't exist than it is to prove that a limit does exist. Okay, because you have to think in 2D, we just have to come from the left and the right. But in 3D, you would have to come from any direction. So we'll start with some that don't exist, okay? So the paths are up to you. There are some easy ones to pick. So if we have our limit as xy goes to 0, 0 of x squared minus y squared over x squared plus y squared, okay? Your easiest paths are along the x-axis and along the y-axis. Okay, so you got to think about it. If you're along the x-axis, y equals 0. Okay, so if we're approaching 0, 0 along the x-axis, we'd be finding the limit, again, as xy approaches 0, 0, but our function would just be x squared over x squared because y is 0. So we just basically rewrite our function for what it would be when we are on this path. Okay, so if we're on that path, our function is x squared over x squared, and the limit would equal 1, and again, as long as x isn't 0. Okay, so that's you pick a path and you rewrite your function as if you're on that path. Okay, so now when we do the y-axis, x is 0. So if we rewrite our function, the limit as x, y goes, and really, I'm going to back, I got ahead of myself here too. We could also write that first one, since we've already taken care of it and y is 0, you can also just do this as the limit as x goes to 0. Okay, y doesn't need to go to 0 because it already is 0, right? So this one too, we could write the limit then as y goes to 0, and our function would be negative y squared over y squared. Okay, so you might see it either way. You might be more comfortable with it either way. It doesn't matter, right? Because, oops, I didn't switch there. Since there is no x in the expression, this is the same as this. You know, I could just as easily write it as the limit as x, y, z goes to 0, 0. Well, I shouldn't use z. Well, no, because it's f of xy, so we're good. Of y squared over y squared, you know, negative. That's the same thing. I can throw in as many variables as I want. They're not even an expression, so it doesn't matter. Okay, I mean, definitely don't do that. There's no reason to add them in, but either of these would be fine. Okay, and your limit there then would be -1. Okay, and again, that's just because that expression x squared over x squared is 1, right? And negative y squared over y squared is -1. There's no L'Hopital's rule or anything in here. That's just going to be 1 or -1 every time. And again, as long as y does not equal 0. Okay, so now really big important thing here is that 1 is not the same as -1, right? So since those limits along the two paths aren't equal, the limit does not exist. Okay, so that limit does not exist. Okay, and I actually have a graph to show you. So as we're getting into some of these 3D drawings, you might want to try some 3D drawing tools. If I haven't showed you already in class these, okay? But this first one is called Calc 3D. And so this is the graph that we were just looking at. And it's a little bit harder to see there, but as we approach 0, 0 along the y-axis, okay, and as we approach it along the x-axis, you kind of see that weird, like, discontinuity in there, it looks like, okay? If you use GeoGebra, this one's a little bit smoother. But you can kind of, if you rotate it, kind of see where there's just some weird stuff going on at 0, 0. That seems here like it's going to 1, maybe, but then when you look underneath it, it's at -1, like it's some weird folds in there that would make the limit not exist, okay? So you can definitely fool around with those two plotters and see what you like, okay? We can do another one now. We do the example, the limit is xy goes to 0, 0 of xy over x squared plus y squared. Okay, now if we do the limit as along the x-axis, okay, then we'd have the limit as xy goes to 0, 0 of 0 over x squared, which that is 0 over x squared would always be 0. Okay, so that'd be 0. We could do it along the y-axis. So x would be 0. And then we would have 0 over y squared. Well, that's also 0. So we didn't get very far with that because it's the same limit. We want to try a different path then. Another good one is along y equals x. So we're going to change our expression so that y equals x. If y equals x, then we would have x squared over x squared plus x squared. So that's x squared over 2x squared. So we get 1/2. Okay, and now as soon as you've got two that don't match, that limit does not exist. Okay, So you can pick any path you want. Another common one would be along the line y equals x squared. Okay. You can pick, if you keep getting the same thing, you can pick it, or the other possibility is that the limit does exist. Okay, and that is the limit, and that's a little bit harder to show. The next one you're going to get here. Oh yeah, the next one does use that one. So another example here. And again, you guys, I told you, if you feel like you've gotten enough examples, you can always go through them a little quicker. I don't want the videos to get too long, but I also don't want to leave anything out. Okay, so xy squared over x squared plus y to the fourth. Okay, now I'm going to kind of skip ahead here a little bit. This one might even be in the book. If you go ahead and try it along the x-axis, right, you're going to have 0 over y to the, 0 over x squared, which will go to 0. If you do the y-axis, you're going to have 0 over y to the fourth, which will go to 0. If you do y equals x, you have x cubed over x squared plus x to the fourth, which is also going to go to 0. Okay, so you're going to get a lot of zeros if you try the ones that we've done already. Now, if you do along y equals x squared, you're also going to get 0, right? If y equals x squared, then you would have x to the fifth over x squared plus x to the eighth. So the limit of that as x goes to 0 is also 0 because of your leading terms. Okay, so if you do x equals y squared, you get the limit of y to the fourth over y to the fourth plus y to the fourth. So that's 2y to the fourth. Okay, and that does end up being 1/2. So if you did it along the x-axis, you got 0. The y-axis, you got 0. Y equals x, you got 0. Y equals x squared, you got 0. Finally, x equals y squared, we got something different to show that the limit then does not exist. Okay, so that was a little tricky one there. Now, if we're going to take a look at another one here, we have the limit is xy goes to 0, 0 of 3x squared y over x squared plus y squared. Okay, now what happens here is everything that you try, it does seem to go to 0. Okay, you're not going to get any way that it doesn't go to 0. So it seems that it exists, but in order to show that it would exist that way, you just have to keep doing every single possible path ever imaginable, which we know is infinite. So you would never be able to actually prove it just by showing that it works. You know, even if you could show that it works along 1,000 different paths, you still haven't proven that it exists. Okay. Now your book goes into a bunch of stuff with delta epsilon notation. Okay, your delta epsilon notation. It is a great skill to have if you're going to take more advanced math classes. It's very old school math to be able to prove limits with delta epsilon notation. I'm going to skip over it because you don't need to use it at all in the homework, on the quizzes, or on the tests. I would encourage you, if you're somebody who's really interested in math and want to go farther with this, to look into it a little bit, and I'd be happy to show it to you. It's one of those things that I come across it like once a year, and I need to kind of show myself again how to do it. But I would be happy to work with you if that's something you're interested in. Otherwise, we can keep moving here. So all of the problems that you guys are going to have to do, you can use the squeeze theorem. Okay, so in your squeeze theorem, remember, is that if f of x is always less than or equal to g of x is always less than or equal to h of x, then the limit is x goes to c of f of x is always going to be less than or equal to the limit is x goes, oh, sorry, that's not right. I'm getting them mixed up with the other one. Okay, if this is true and the limit as x goes to c of f of x equals the limit as x goes to c of h of x. Okay, so if and then, let's say that equals L. The limit as x goes to c of h of x, nope, g of x, the one in the middle, is also L. Okay. So what you do here is you kind of isolate a piece that you can find is always between like 1 and -1, or even 0 and 1. Okay. So what you want to look for, and the two that come up the most are x squared over x squared plus y squared. That's always going to be less than or equal to 1. Okay, and it's always going to be greater than or equal to 0 as long as x isn't 0. So it's always, I mean, I guess I could say greater than or equal to 0, right? You can't, if x is 0, it is 0. Okay, otherwise the numerator is always less than the denominator. Okay, another one that you will see is x over the square root of x squared plus y squared. That is always less than 1. Okay, at best, if y is 0, then your numerator equals your denominator. If y is anything other than 0, your denominator is bigger than your numerator. Okay, and in this case, your numerator could be negative. Okay, so both of these show up a lot. Okay, and in both of them, if y equals 0, then the expression is 1 or -1. If y is anything other than 0, the expression is less than 1, because the numerator will always be less than the denominator. Okay, so you can kind of convince yourself of that. And I mean, we could switch the x's and the y's too. We could have a y squared on top. Okay, like y squared over x squared plus y squared is also always between 1 and 0. Okay, but these are the ones to look for. Okay, so what we can do with that then is that we have that right here. Okay, so I'm going to rewrite that guy down here. Okay, we're trying to find the limit again is xy goes to 0, 0 of 3x squared y over x squared plus y squared. Okay, so since x squared over x squared plus y squared is always between 1 and 0, then 3x squared y over x squared plus y squared is always between 3y and 0. We just multiplied everything by 3y to get our expression that we wanted. Okay? So we found that key piece at x squared over x squared plus y squared and kind of isolated it. And then we added in what was left. So we got from here to here by multiplying by 3y. We got from here to here by multiplying by 3y. And we got from here to here by multiplying by 3y. Okay, so now we can use our squeeze theorem. The limit as xy goes to 0, 0 of 0 is 0. And the limit as xy goes to 0, 0 of 3y is also 0. Okay, so therefore, the limit is xy goes to 0, 0 of 3x squared y over x squared plus y squared must also equal 0. Okay, so you need to make sure that you're showing that kind of hierarchy here. You need to show that you're showing the limits of the low one and the high one, and then you can find the limit of the middle one. okay? I feel like my screen is getting a little bit glitchy, so I'm going to stop here. That's the end of the limit section. So then I'm going to make a second video for continuity.